We're going to be looking at linear inequalities, which means the variables are raised to the 1, but they will be in 2 variables. And by the way, you already know how to graph linear inequalities with 1 variable. But I don't know that your math teacher has ever just pointed out to you that that's what you're doing. If I have the following, if I have that's a 10, not a 1.0. This is an inequality because of the less than or equal to. And it's linear because x is raised to the 1. And it contains 1 variable, just x. If I solve that, I subtract 1 from both sides and get 3x is less than or equal to 9, I get x is less than or equal to 3. Would you be in agreement with that? How do you graph that? And guaranteed, you've graphed this before, but maybe you haven't called it a graph. What do you do? Sure, we just draw a number line, and we can use the x-axis. I'm just going to draw a number line to begin with. But what we would normally do is say this is x, this is 3, so this is a graph of the function. Well, if you were to graph that, and I'm going to show it to you on an actual grid. If I said graph, forget about this other stuff. If I said graph x is less than or equal to 3, then it looks like this. But it's a one-dimensional graph. It's got no y to it. So when we graph these linear inequalities with 1 variable, most of the time you don't even use the Cartesian grid, right? You just do that. But that is a graph. A number line is a graph. It's just a one-dimensional graph. Go back to the beginning here. So you already know how to graph inequalities with 1 variable. Today we're looking at linear inequalities with 2 variables. And we're also going to be understanding the significance of what's called a test point. So as a warm-up, I have an inequality there. 2x minus y is greater than 1. It's linear because x is to the 1 and y is to the 1. It's an inequality because there's a greater than symbol. It's got 2 variables because it's got 2 variables. Your job right now is to find out which ordered pairs in this list make the inequality true. So for example, if I put 2 in for x and 3 in for y, what I would get is 2 times x, which is 2, minus y, which is 3, and I'm finding out whether I get a number that's greater than 1. If I get a number that's greater than 1, you're going to circle the ordered pair. If it's not greater than 1, you're not going to circle it, you're going to cross it out. And in this first case, I end up with 1. Is 1 greater than 1? Is that a true statement? No. So this point is not a point that makes that inequality true. And what I want you to do is take a few minutes, everybody, and determine which points do. And we're not going to be doing it this way all the time. We're just learning from this method how we can do it quicker. And I'm going to double check all of these when I get a second. So I'm seeing one person in agreement. You know, if I were writing an exam, I were a student in high school, I would want to be using my calculator, but I was just doubling x and subtracting y in my head, and I'm starting to see 3 or 4 people, 5, 6 people agree. Those are the points that make the inequality true. Did you notice that there were a bunch of points that were, I would call them on the edge, where you ended up with 1 is greater than 1? Those are not a solution. If everybody, this was the inequality, which it is not, then those ones that where we had 1 on one side and 1 on the other side, we would include those. And that becomes important for later. So now what we're asked to do here, how many different ordered pairs exist that can make the inequality true? There's an answer to this question. What do you guys think? 5? That's it? No more ordered pairs that would make it work? What if I chose, I mean, think about this inequality. What if I chose x equals 1,000,000 and y equals 1? Wouldn't 2x minus y still be greater than 1, or greater than 0 rather? Or greater than 1, I guess it is. Okay. So what's the answer to the question? Infinity, right. There's an infinite number. Now here's the problem though. When you graph an inequality in one variable with an infinite number of solutions, you just draw a line in the direction that covers all of the numbers. We can't do that because this is two-dimensional. So the next part of this warm-up is going to explain to you how we graph these to see visually what the solution is. We're asked to plot the line 2x minus y equals 1 using a dotted line. Okay, that's the first point, and you'll know why it's dotted in a minute. So we're graphing y equals 2, or 2x minus y equals 1. I want you to notice the line that we're graphing has an equal sign, but that's not the inequality. The inequality is a greater than sign, but we're asked to graph the equals. Well, I'm going to rearrange this for y. Y is equal to 2x minus 1. We don't need to use a table of values. We know that the line is going to pass through, and don't draw anything just yet. It's going to pass through -1 on the y-axis, and it's going to have a slope of 2, because there's a 2 in front of the x. So that means from this point right here, I'm going to go 1 to the right and 2 up. So it's going to pass through here and here and here. And you're going to draw a line there, but you're not going to draw a solid line. You're going to draw a dashed line. So this is what we need to draw. And now what we are asked to do is plot all of those points at the top of the page. And you should be using a ruler for this. We want to plot all of those points at the top of the page. And if the point was a point we circled, we want to put a solid dot. Yep.
Can I have a ruler?
Oh, I'm sorry. Of course. Did you not get one either, Gabrielle? Does anybody else need a ruler? Okay. So, for example, and I'm going to freeze on the other screen my data points so that I can see them to refer to them. For example, that 2, 3 is not a point that makes the inequality true. So when I plot 2, 3, I'm going to put it there. You remember I told you some of the points were just on the edge, so to speak? Look where that point lands. It's on the line. On the other hand, 4, 4 was a solution. One, 8 was not a solution. 5, 10 was not a solution. I'm going to extend this line to make a point in a minute. Is that 3, 6? I can't read that. Next one is 3, 6. Good. And it's not a solution. So 3, 6. We also have 5, 9, which is not a solution. And then we have 1 comma negative 1. Then negative 2, negative 6, which is not a solution. Sorry, which is a solution. Oh, just a second here. 1 comma negative 1 is a solution. So is negative 2, negative 6. These are solutions. For negative 4 and negative 7. Negative 4, negative 7. I mean, you might get the idea here, but for completeness sake, I'm going to complete it. Negative 5, 5. Negative 4, 10. Negative 10 is a solution. Couple more. Negative 2, 3. Didn't we do negative? Oh, negative 2, 3. There we go. Negative 3, negative 9. Negative 3, negative 9. And lastly, negative 1, negative 3. How do I do craning my head to read those properly? Here's my question for you. What do you notice about all the points that are solutions? Jay? They're underneath the line. And that's good. I'm glad you said they're underneath. I'm glad you didn't say they're to the right of the line. We want to think of above and below. The solutions here are any points that are below the line. What is important about the points that are not solutions? They're either above or on the line. Can you tell me what our graph, and I hope you get this, but how would our graph would be different if the inequality was not, so we're building the inequality here, 2x minus y is greater than 1, right? In an alternate universe, if I changed the question and it was this instead, what would be different on the graph? What's one thing you think would be different? Ashira?
The points on the line would become.
Those would be solid. Good. What else do you think would be different? We'd use a solid line. The dotted line is telling you that that's not a solution. But if it could be equal, then we would have a solid line here. So how is it, looking at this now, going back, I want to delete this page because this is not what we're talking about. What do you notice about the ordered pairs that are part of the solution? They lie below the line, the dotted line. How can I communicate that all of the points below the line are solutions? Well, I can just shade it in. This is the solution to the inequality. That's the solution. It's telling you any point in that shaded region is a solution, but not where it's not shaded and not on the line because the line is a dotted line. Does that make sense? Any questions there? All right. So how can all of the solutions be shown? Shade. Shade the solution region. And this is the difference. When you draw a number line showing the solutions in one variable, it's just a line with an arrow pointing left or right for x. When you have a two-dimensional, you shade a region. Why were we instructed to graph the line using a dashed line? Because that doesn't include equal. If the inequality doesn't include equal, you're going to use a dotted line or a dashed line. If the inequality does include equal, then what you're going to do is you're going to use a solid line. There's a shortcut here. There's a couple of ways we can decide which side to shade. And we're going to look at both methods. So the solution to I'm just going over what's in your notes. The solution to a linear inequality is represented by a shaded region either above or below the line. If the inequality contains or equal to as part of it, then we want a solid line. If it does not, we want a dotted line or dashed. And in order to determine which side you shade, you simply use a test point. And that's what we're going to learn here. So sketch without using technology the following. Let me ask you a question. Are we going to have a solid line or a dotted line here? Solid, right? Because there's an equal to in there. So we, in our head, say to ourselves, let's not worry about the inequality, let's graph that line. We go back to grade 10 math, start rearranging for y. I'm going to have to divide both sides by 2. And are we in agreement on that rearrangement? Good. You have a question? Oh, yeah, I'm sorry. I forgot to unlock that. There you go. So this line has a y-intercept of 6, and it has a slope of -3/2. -3/2 as a slope, just to remind you, means you go 2 to the right and 3 down. I didn't teach any of you Math 10, but what I would tell my Math 10 students is the run is always positive. The run is always to the right. And if the slope is positive, you go up. If the slope is negative, you go down. So all we have to do is lay down our ruler over 2 and down 3, over 2 and down 3, and draw a solid line. 2 and down 3. There. And I admit I'm being a little lazy. We should, for any line, have arrows on the end. Now, it's a solid line because of the equal, and the fact of the matter is it's either shaded above or below. It is. Listen very carefully to this. If you shaded it above just by flipping a coin and somebody else shaded it below, one of you are right and one of you are wrong. How do you decide? You decide by using a test point. You pick a point that is either above or below and see if it makes it true. And anytime I can, everybody, anytime I can, I choose the origin. Because putting in 0 for x and 0 for y is a breeze. If I put in 0 for x and 0 for y, I get 0 plus 0 is less than or equal to 12. I get 0 is less than or equal to 12. True or false? True? Then the point that I've picked is on the side that should be shaded. It's that simple. We're going to shade here. If, when we put in 0, 0, we get a false statement, then we don't shade that, we shade the other side. Now there is a way to tell that it's shaded below that I'll get to in a bit without using a test point. Any questions with 1? This is really simple stuff. You have to be able to graph a linear function. All right, 2. Will this be a dotted or a shaded line? Nate? Dotted, good. Did I say dotted or shaded? Yeah. Will it be a dotted or a solid line? Dotted. Okay. We ignore the inequality and we say to ourselves, what will this graph look like? So I'm going to rearrange this for y. I'm going to move the y to the right and get 2y as 5x minus 14. So I divide everything by 2, and I get 5/2 x minus 7. -7 is the y-intercept, so we're going to draw our line through this point, although we're not going to draw a solid line when we do so. The slope is 5/2, which means you go over 2 and up 1, 2, 3, 4, 5, over 2 and up 1, 2, 3, 4, 5, etc. Roughly. Now we shade it. How many of you, I'm just going to throw this out here now. How many of you maybe, and if don't lie, I mean be honest with me. How many of you maybe knew that this would be shaded below because there's a less than in the equation? How many of you suspect that now? Okay. Keep that in mind. Let's pick a test point. I'm going to pick this one. Again, putting in 0 for x and 0 for y makes your life so much easier. If I do that, I get 0 minus 0 is less than 14. 0 is less than 14. True. Which means that test point is a solution. Which means the solution is shaded above. Why? And I'm doing this intentionally. I pointed out to you in the previous question there was a less than, and it's shaded below. Why, even though this has a less than, am I shading above? Jay? Oh, interesting. Yeah. The last one had a negative slope. This one has a positive slope. I'm going to say that that isn't always going to be the case. There's something else going on here. The answer is that we had to move the y to the other side to make it positive. So when you look at this equation here, it actually is the following inequality. It's actually y is less than or equal to negative 3 halves x plus 6. Y is less than. Y is less than. It's lower than, which is why it's shaded below. But if you rearrange this inequality for y, not with the equals, but you rearrange the inequality, you're going to get this. But if you look at what that's telling you about y, y is greater than. It's above the line. So that's the other way you can do it. I like the test point, though. Let's try one more. I'm going to leave the inequality symbol in here this time. Divide everything by 3. Can we agree on that rearrangement? Okay, so based on what I just said, where do you think we're going to shade here? Are we going to shade above or below? Above, because it says y is greater than. If we had to move the y over, then we would read it backwards and we would shade on the other side. We're going to have a solid line. The y-intercept of this line is 4. This is your y-intercept. Your slope, of course, is negative 4/3, which means we go 3 over and 4 down, 3 over and 4 down. Draw your solid line. So, just to let you know, I would never ask you on an exam or an assignment to explain why we're shading there. So I guess you could flip a coin. If you wanted to, you could try this test point. And I put 0 in for x and y. I get 0 is greater than or equal to 12, which is wrong. It's false, which means that point I've chosen is not a part of the solution region, which means we shade the other part. We okay there? Okay. I want to go through one other thing. We can do this on our calculator. And I don't care if you draw a masterpiece here. But the first thing we have to do is rewrite this inequality in terms of y. So remember, I'm going to force you to do something here. I'm going to force you to move the y's over and read it backwards. I do not want you leaving it as negative 4y and dividing by negative 4. I guess you can, but then you have to remember that seldom used rule of switching the sign. So I get 3x minus 12 is greater than 4y. I divide everything by 4, and I get 3/4 x minus 3 should be greater than y. And I read it the other way. So my inequality is this. Y is less than 3/4 x minus 3. And I'm going to graph that on my graphing calculator. There it is. So y, I can't change this equals to less than. I'm just going to put y equals 3/4 x minus 3. I can't remember if this is this class or another class I'm thinking of. Have we had this discussion why I want to put the 3/4 in brackets? It just looks right. I don't need the brackets, but if I don't, it looks like I'm dividing by 4x. So the first thing to note is that when you graph these inequalities on your calculator, there's no way to tell it to shade and do a dotted line. Okay? We need to know that this will be a dotted line because there's no equals. But if you scroll over past the y1, you can control the type of thing that is graphed. So right now it graphs a line. I can graph a thick line. If I hit enter again, I can graph that. Well, wait a minute. Look at that for a second. What that is a triangle that looks like this. You've got a triangle on the screen that looks like this. Well, that is shading above. So if I want to shade above, and I believe I do, don't I? No, I want to shade below. Then I hit enter again until I get a triangle at the bottom. And now I go graph. I'm going to go zoom 6 because I don't know what my window settings were. And that's the picture. Okay. Again, you want to be careful here because your graphing calculator, unfortunately, automatically assumes it's less than or equal to. It won't do a dotted line. Okay, there's no way to tell it to do a dotted line and do that shading. Yeah.
How did you get that?
So where my y is, Owen, I go y equals. I scroll over here, and you should see just a basic line there. Just keep hitting enter once you're over there, and that line will change to a thick line, and then to dots, and then triangles, and we want that triangle that's below. You know, I don't know what you want to draw there. I'm going to be a little bit lazy and say that's what the picture looks like, right? You don't need an accurate diagram. Just draw your line in approximately where it is on the screen and shade below. Just one more? Two more. You know, I think you get the idea. The first one we just did here involved moving the y over to the other side, so we had to read it backwards. Let's do C. Let's skip B. Let's do C. The 7y stays the same in the same place. And this should be telling you that when you divide both sides by y, you're going to be shading below. Right? Otherwise, you have to pick a test point. Negative 2x plus 12. Divide everything by 7. Negative 2/7 x plus 12 over 7. Luckily, we don't have to do this on paper. You know, the y-intercept, whoops, the y-intercept of 12/7 and then a slope of negative 2/7. We don't need that. You just enter it in your calculator and shade below. Looks okay. We'll do B as well. It'll only take a second. That's what it would look like. With B, of course, you have to move the 4y over to make it positive, giving us 1/4 x plus 12 over 4, which is 3. Are we going to shade above or below? Craig, what do you think? Above, good. Because when we read this in terms of what y is greater than. We're reading it right to left. So you just enter that in your calculator and choose the triangle that shades above. Again, there's no way to distinguish whether it's a dotted line or a solid line. I'm just going to put 0.25x rather than 1/4 x plus 3. Graph. I guess I could have changed that shading option right now. We want a graph so that it's shaded above, and that's what it would look like. So that's what you can draw. And again, it doesn't have to be perfect. Just draw a line in the approximate position that it appears on your screen, and then shade above the line. That's it. That's all in a nutshell. What we're going to be looking at are quadratic inequalities in 1 and 2 variables as well. And strangely enough, quadratic inequalities in 1 variable is more complicated than quadratic inequalities in 2. Anyway, on page 472, questions 1 through 5.